Welcome everyone. My name is Aarti. Thanks for joining us today. As business processes grow in complexity, modern application developers look to distribute work across multiple independent services. While this can help with scale and accelerate development, it introduces challenges with coordination, such as state management, orchestration, and increased failure handling requirements. In this talk, my colleague Anita and I will show you how AWS Step Functions can help solve these challenges and reduce the burden on application developers. So let's start by taking a look at the common workflow requirements. Workflows are made up of a series of steps with the output of one step acting as input into the next, also called state machines. Now, business workflows exhibit different patterns. Some steps must be sequential, while some can run in parallel. Workflows can follow different paths based on input criteria. Now, as the workflow progresses through steps, it must not lose state information. It must also be able to handle and recover from failures. From an operations perspective, workflows must be scalable, easy to build and operate, and auditable. Now, you can implement these requirements in your application with custom code, or you can offload this to AWS Step Functions and focus on business logic. In the following sections, we will dive deep into the capabilities of step functions that can address these requirements. Let's look at the basics first. You can define workflows in JSON using Amazon States Language or ASL for short. You can also use infrastructure as code frameworks such as AWS SAM or Serverless for this. Once step function is deployed, you can monitor executions using the AWS console and native Amazon CloudWatch integration. Now, the core building blocks of step functions are states and transitions. A state can be of many types. Almost all step functions have a task state because all work in your state machine is done by tasks. Other common states are choice, which allows you to implement branching logic, wait, which lets you pause the workflow, and parallel, which allows you to run tasks concurrently. Now, transitions link the states together, defining the control flow for the state machine. Now, there are two main types of step functions, standard and express. Now, standard workflows are ideal for long-running, durable, and auditable workloads. They run exactly once unless you specify a retry behavior. So they are ideal for use cases such as IT automation, order processing, billing processing, and ETL. Express workflows, on the other hand, are ideal for high-volume event processing workloads, such as IoT data ingestion, streaming data processing, and mobile application backends. So now, with the basics out of the way, let's look at the business scenarios that step functions can help with. The first is task automation. A great example here is Zalora, Asia's online fashion retailer, who used AWS Step Functions to automate the refresh of their SAP HANA environment. So this has not only brought down the refresh time from 5 to 2 days, but it has also improved the quality of refresh. The second is data processing. So genetic testing provider Myriad Genetics uses step functions to quickly and accurately process enormous amounts of gene sequencing data for clinical testing. Finally, step functions are a great way to modernize monolithic applications and orchestrate the data flow between application components. So Singapore-based social music platform BandLab use step functions to modernize and orchestrate their live streaming workflow. The rest of this talk will focus on architecture patterns for each of these use cases. So let's start with task automation. So we have Zendesk as the customer support platform here. Our tickets are assigned an SLA based on their priority. Now, we want to improve this customer support workflow to expedite tickets from unhappy customers by automatically escalating the ticket priority. So we've integrated Zendesk with Amazon Event Bridge, which is a serverless event bus. So Zendesk will publish all ticket events to Event Bridge. Next, we use an Event Bridge rule to filter ticket creation events to trigger step function. Now let's say an unhappy customer creates a ticket at normal priority. So step function retrieves ticket details such as the subject and uses Amazon Comprehend to detect sentiment. If negative, it'll kick off another step function. Now this child workflow will tag the ticket and bump the priority to high and return the control to the parent workflow. Now the parent will wait for a duration defined by the SLA for high priority, which is 4 hours in this case, and trigger the child workflow again. Now if the ticket is not resolved, it'll escalate the priority to urgent. When control returns to the main workflow, it sees that the ticket is at the highest priority and will end the workflow. So now let's look at the step function capabilities that we are leveraging for this pattern. So we saw 2 ways to trigger step functions, using Event Bridge and step functions itself. But you can also trigger step functions from API Gateway, which is a managed REST API, Code Pipeline, which is a managed continuous delivery service, IoT Rules Engine, which is a managed service to process IoT data, and finally Lambda using the Start Execution API call. Or you can always trigger using the AWS console or the AWS CLI. Now the pattern of invoking a step function from another step function is known as nesting. So nesting lets you break down large workflows into smaller ones and create reusable libraries of code. Now this in turn simplifies management and development. Now the snippet of ASL code on the left shows how you can define nesting. So there are 2 things to note here. The first is that our child workflow is an express workflow, and there are 2 ways to invoke it. So the .sync suffix for resource specifies a synchronous execution. This means a step will wait for the workflow to complete and then return the result. The default is asynchronous execution. The :2 in the end indicates that we want the output as JSON instead of string. Now the second thing to note is that the special parameter AWS Step Functions started by execution ID, when passed to the child workflow, allows you to associate the 2 workflows for end-to-end tracing. The retry block allows configuring retry behavior to recover from transient errors. So let's look at the retry behavior for the ticket info step. If the first call fails, control flows to the retry block. Step function waits for a duration defined by interval seconds parameter, which is 3 seconds in this case, before retrying. Now if this retry fails, control returns to the retry block again. But this time, step function uses the backoff rate. This is the multiplier by which the retry interval increases during each attempt. So step will wait for 1.5 times 3 seconds, which is 4.5 seconds, before trying again. Now if this fails as well, control once again returns to the retry block, but step will see that we've reached the max retry attempts, which is set to 2, and will fail the workflow. So this shows how you can implement some sophisticated error handling with 0 lines of code. So now this concludes our first use case. Now let's look at a pattern for the next use case on data processing. The business intelligence team, or BI team for short, wants to correlate marketing events and sales revenue. Now this is an example of batch-based data processing because we are looking at data collected over a period of time. Let's say the sales revenue data and the marketing events data are both stored in an S3 bucket. Now this raw data must be processed and transformed before we can generate the report for the BI team. So this workflow is also triggered by Event Bridge, but this time it is a cron schedule. So this step will be triggered at 12 p.m. UTC every day. A Lambda function will first list all the files and trigger parallel processing for all using AWS Glue, which is a serverless ETL service. The processed files are written into a new S3 folder. The next Glue job joins the intermediate data files to generate the final report. An email notification is then sent to the BI team using Amazon SNS. So again, let's look at the step function capabilities used in this pattern. So the key capability we leveraged here is the parallel execution of tasks. Now step functions has a parallel state, but parallel states work well when you have a fixed input. That is, when you know the number of branches beforehand. Now if the sales data is reported by country, it is easy to predict the number of sales files and it's unlikely to change often. But on the other hand, the number of marketing data files depend on the number of campaigns run, and this can fluctuate widely depending on the marketing calendar. So the map state is ideal for such dynamic parallelism. So map state expects an array as its input and creates a branch for each element in the array. Now you can limit the concurrency by specifying max concurrency. Now one reason to do this is to ensure you're not taking up all the capacity for Glue in your AWS account and affecting other teams. So in this case, if we have 5 marketing data files, the first iteration will process 3 files and the next one will process the remaining 2. But the workflow will advance to the next step only after all the files have been processed. Now there are 3 ways in which step function integrates with a service. The first pattern, run a job, will wait for a request to complete before progressing to the next state. So you define this by specifying a .sync suffix to the resource arm. So a good use case for this is the join step, because we cannot join the data unless the previous processing steps have completed. The next integration pattern is request response. Now this is the default pattern. So step functions only waits for an HTTP response from the API call and progresses to the next step. An example of this is the integration with SNS to publish notification of report completion. So step will invoke the publish API of SNS, but it won't wait for the message to be delivered to the subscribers. Now this pattern can be used with all AWS services that integrate with step functions. You need to note though that if you're using Express workflows, this is the only pattern supported today. Now the last pattern is await callback, which we've not used in this architecture. But callback tasks call an external resource with a token and pause the workflow till the token is returned with the send task success or send task failure API call. So you define this by specifying a .wait for task token suffix to the resource arm. Now this is very useful for workflows involving human interaction or dependencies on applications outside AWS, such as third-party APIs or legacy applications hosted on-premise. So this pattern is also supported by the AWS services shown here. So now this concludes the second use case. Now the architecture patterns for these 2 use cases have also demonstrated how you can modernize workflows with serverless components and orchestrate flow of data by offloading state management to step function. However, often in the microservices world, state is persisted in independent databases. Transactions are consequently distributed across databases. Now this introduces new challenges such as handling transaction rollbacks. I will now pass it to Anita to take you through how step functions can address the challenges posed by the last 2 use cases.
Thanks, Aarti. Hello, everyone. I'm Anita. I'm a Developer Specialist Solutions Architect here at AWS. I'm part of the Developer Acceleration team, DevAx team. In our team, I work with the customers to help them understand how to build secure, reliable, and scalable systems on AWS. I'm also a full-stack developer with several years of domain experience in the financial services industry. I have designed and implemented applications of various architectures: web applications, REST APIs, database programming, UX design, and batch processing, just to name a few. I also have a lot of experience in developing multi-threaded applications and asynchronous processing. Today, I'm going to speak to you about how you can use AWS Step Functions to implement microservices communication and the Saga Orchestration pattern. Let's start by taking a look at what happens when a monolithic application is migrated to a microservices architecture. The monolithic application is split into smaller services called microservices. Microservices are organized around business capabilities with a separate database per microservice. The services are loosely coupled and they use asynchronous messaging to communicate with each other. These services are independently deployable. Let's imagine there are 2 microservices, order service and fulfillment service. Order service completes processing and notifies the fulfillment service. In a normal scenario, event notification pattern would be used to notify the fulfillment service. Now the fulfillment department staff notice something strange. They see the payment status is still pending when the order arrives for fulfillment. After some investigation, they find that there is a short delay in the payment status update in the database which has caused this issue. A wait state has to be introduced before fulfillment to resolve the issue. Event notification is a fire and forget pattern. It emits an event stating that a command has been executed, but it does not allow the users to control the timing. So how can you introduce this delay when using event-driven architectural patterns? This can be easily solved using the AWS Step Functions. AWS Step Functions allow us to introduce a wait state when the source service emits an event. The workflow waits for 10 seconds in this case and then starts the fulfillment processing step. As you can see, you can get more control over the service interactions by using the AWS Step Functions. This concludes our third use case. I'm now going to discuss how you can use the AWS Step Functions to implement a very important pattern in the microservices architecture. As I mentioned earlier, microservices communicate through events to indicate the process changes. In the microservices world, one user command may need to be executed by multiple services before it is complete. Imagine that a customer is placing an order in an e-commerce application. You can see that the order gets processed by order service, inventory service, and payment service before it is confirmed and sent for fulfillment. You see the happy path on the screen. There are no failures in the workflow and the order gets placed successfully. If you notice, this is an example of a distributed transaction with polyglot persistence. The transaction data gets stored across different databases and each service writes to its own database. Let's imagine now that there was a network failure and the payment gateway has timed out. So the last step in this workflow has failed. At the time of failure, the order database and the inventory databases are already updated. The status is set to fail to indicate failure to the downstream systems. But if you look at the data, it is now inconsistent. Order state is set as ordered, inventory has been decremented. There is no way to correct the data, and there are no options to retry the processes that have failed. We are actually missing something here. In relational database, we get ACID transactions: atomicity, consistency, isolation, and durability. If a transaction fails in a relational database, the transaction gets rolled back. But in distributed systems like microservices, two-phase commit is not an option as the transaction is distributed across various databases. In this case, the solution is to use the Saga pattern. By using the Saga pattern, if any transaction fails in the workflow, the Saga executes a series of compensating transactions that revert the changes that were made by the preceding transactions. Let's imagine that a customer places an order when an item was low in stock. Another customer's order gets fulfilled in the meantime, and it goes out of stock after the order has been placed. As we all know, this can happen when multiple customers are trying to purchase the same item. In this case, the update inventory step will fail in the workflow. The orchestrator will now execute the compensatory transactions. It will run revert inventory, remove order steps, and return the status as failed. These compensatory transactions ensure that the data integrity is maintained. The inventory reverts to original levels and the order is reverted back. As you can see, for every action that makes a change to the data store, there is an opposite action that compensates the change in case of a failure. It's almost like Newton's third law. For every action, there is an equal and opposite reaction. A failure that happens in the last step, payment service in this case, will cause all the compensatory transactions to be executed before returning a failed state to the event bridge. If all the steps succeed, a success state is returned to the event bridge. We can now see how this can be implemented using AWS Step Functions. The individual steps call a Lambda function to perform the task. The step transitions are defined in the Amazon States language. The state mission makes it very easy for us to configure the compensatory transactions in case of failures. Here, you can see how the Saga orchestration has been implemented with the Amazon States language. This shows the payment processing steps of the orchestration pattern. If the payment does not succeed, the payment is reverted and a failed state is returned to the caller. This can be easily extended to define the orchestration of a complex transaction. Now we have seen all our use cases. Let us now see a demo of the Saga orchestration pattern. In this demo, I'm going to show you how you can implement the Saga orchestration pattern using the AWS Step Functions. I will show a distributed transaction success path and a failure path. While demonstrating the failure workflow, I'll show you how the data in the DynamoDB database is reverted to a consistent state. Finally, I'll load test the step functions workflow using BlazeMeter and show you how the step functions scale out during peak load. I'm using AWS Lambda to implement the microservices and Amazon DynamoDB as the data store. I have already created a REST API endpoint using Amazon API Gateway to trigger the step functions workflow. Let me start by showing how the step function console looks like. Here you can see the state machine definition and the visual workflow. If you see here, the place order step is of type task. It calls the Lambda function called place order Lambda. If the order is placed successfully, the Lambda function returns a string called order placed. Otherwise, the Lambda function returns a string called error. Once that step is executed, the workflow now executes the next step, which is the isOrder placed step. If you notice, this type is choice, and the decision is made by depending on the output from the previous step. If the output from the previous step is order placed, then the next step is defined as update inventory. Otherwise, the step function exits with a failed status. On the right side, you can view the visual representation of the states we have defined. I'm now going to execute this workflow from Postman and show you what happens when the state machine runs successfully. I'll trigger the API from Postman tool, and this will in turn start the state machine. I've already set up the API using Amazon API Gateway. In order to simulate the successful and failure runs, I'm sending an extra parameter called fail at stage along with the necessary parameters item ID and customer ID. For this run, I'm sending the fail at stage as none, which means that all the states should run successfully. The body of the request is in JSON format. When I click on send, the API triggers the step function workflow, executes it, and returns the status as 200, which indicates success. Let us now see what has happened in the step function console. You can see that a new execution has been created and it has succeeded. I'm now clicking on the execution to see what steps have been executed. You get to see a graph inspector. You can click on each step to see the step input and output. If I click on the step input and output tabs, you can see the relevant order status as order placed and inventory updated. I'm now going to simulate a failure workflow and show you how the Saga Orchestration workflow preserves the data integrity of the data store. Before executing, let us first check the inventory levels in the DynamoDB database. As you can see, there are 9,999 pieces of soap in the database. For this run, I'm going to send the fail at stage as update inventory, which means that the workflow should fail at the update inventory step. In this case, the inventory level should be reverted back to normal by the orchestration workflow. Let us now see what has happened in the step function console. You can see that a new execution has been created and it is running. In the graph inspector, you can see the update inventory step has failed and the workflow is waiting for 30 seconds. This is the DynamoDB console. I refreshed it and you were able to see that the inventory level was deducted and it now shows as 9,998. I have now switched back into the step function console to see the revert inventory step. Now the execution has been done. When I refresh again, you can see that the items in stock has been updated back to 9,999, preserving the data integrity. AWS Step Functions makes it very easy for us to implement the Saga orchestration pattern. With simple steps, the compensatory transactions can be configured to protect the data integrity and consistency. I'm now going to show you how the AWS Step Functions scale out during peak load. I have already configured the load test to simulate the usage of 10 users for around 3 minutes. The test will send more than 2000 requests for 3 minutes. Now the load test is actually running. Let's see what happens in the step function console. You can see the scaling out here where thousands of executions are now handling the incoming requests. The executions are running now, and the DynamoDB database is able to handle the incoming requests without any contention. If you see that the items in stock have been deducted, which means that all those executions have succeeded, and there are more executions coming in, and step function is actually able to scale out to the number of executions that are coming in. New instances, new executions are being created here. This shows the load and the response time in the BlazeMeter tool. If you see here, the output shows that the response time remains constant despite the thousands of executions. Today, we discussed about the various features of the AWS Step Functions and how they can be used to split the workflow from the execution logic. AWS Step Functions orchestrate a series of individual serverless applications by managing sequencing, decision making, parallel executions, error handling, waits, and retries. Automatic scaling helps to ensure the performance of your application remains consistent. AWS Step Functions integrate with a wide range of AWS services: AWS Lambda, Amazon DynamoDB, Amazon SQS, Amazon SNS, AWS Glue, Amazon API Gateway, AWS CodeBuild, just to name a few. We have seen some of the use cases of how the service can be used in the real world. We also saw the demo of the Saga orchestration pattern using AWS Step Functions. If you want to learn more about the AWS Step Functions and AWS services in general, I suggest that you explore the various training and certification options. To gain more confidence and hands-on experience with AWS, access the digital training built by AWS experts. We hope you enjoyed the session and thank you for being here. Please help us make the future editions of AWS Summit better by completing the session survey. We look forward to seeing you the next time.